Okay, welcome to Geotechnical Engineering Design. This presentation will deal with soil pressure, which is an important concept in geotechnical engineering. So we are going to start introducing probably the most famous principle in soil mechanics and in geotechnical engineering, the principle of effective stress. The effective stress is defined as the difference between the total stress and the water pressure. As you know, the water pressure is a stress as well. So this equation, this simple equation, is consistent because every factor, every term, is expressed in unit of pressure. For example, we can use kilonewton per square meters. So we have defined this because in soil mechanics and in geotechnical engineering, all the important changes as deformations and production of stresses are related with the effective stress when we are dealing with saturated soils. For unsaturated soil, there are equivalent expressions of the effective stress, but they are not accurate sometimes because this concept works pretty well in saturated soil, but in unsaturated soil we still doing research in order to find the definite relationship between a sort of effective stress that work for every problem. But let's consider we are in the world of saturated soils, so we are going to use this principle to show how to evaluate the effective stress in a practical case. For example, if we have two layers of soils, let's say a first layer of 4 meters and 30 centimeters of a clay with the properties you can see on the screen, so a dry, a specific weight of 17 kilonewtons per cubic meter, and a saturated unit weight or a specific weight is the way to say it, of 20 kilonewtons per cubic meter. And we have as well a second layer of sand under the clay of 3 meters, and the sand presents as a property a saturated unit weight of 19 kilonewtons per cubic meter. In the case of the sand, we are presenting only the saturated specific weight because we have as well a water table, as you can see in the figure, that is located 2 meters from the surface of this soil, and then the sand layer is underwater, so will remain saturated in our analysis. The layer of clay is saturated under the water table, and even we can consider that it's saturated over the water table because the capillary effects. But this is not the video to discuss about this topic. This video is about the calculation or determination of the effective stress in a simple exercise like this. So in the first place, we are going to start calculating the values of the water pressure and representing them in a diagram of pressure. So for doing that, we are going to use as a reference this vertical axis in black you see here, and we are going to use 4 different points, 1, 2, 3, and 4, to establish the values of the different element that we are going to use to determine the effective stress at the end. So in terms of water pressure, if we analyze the points 1 and 2, so we are at this point and at this point, obviously because there is no water on top of these points, the water pressure is equal to 0. So we can just add these 2 points in here to represent in this diagram that the water pressure is equal to 0. If we go to the next point, let's say the point 3, which is the interface between the clay and the sand, we find that we have a column of 2.3 meters of water, and we know that the specific weight of the water is 10 kilonewtons per cubic meter. This is the reason why we say that the pressure at the point 3 is 10 kilonewtons per cubic meter multiplied by 2.3 meters is equal to 23 kilonewtons per square meter. And we can sketch this diagram, this linear diagram of hydrostatic pressure that starts at 0 at the water table level and increase until 23 when we reach 2.3 meters in depth. The next point to be analyzed is the point 4. We are at the end of the layer of sand, and then we have on top of this point 5 meters, 0.3 of water column, and this is the reason why the water pressure is equal to 10 kilonewton per cubic meter multiplied by 5.3 meters is equal to 53 kilonewton per square meter of pressure. And this is the hydrostatic diagram of distribution of pressure of water for this exercise. The next step is the analysis of the total stress. The total stress will be affected by the self-weight of the soil in the different layers, and this is what we are going to calculate now. So in the first place, before doing the point 2, at point 1, because we are on top of the surface of the ground, and we are going to consider that the atmospheric pressure is equal to 0, then the total stress at the surface of the soil is equal to 0. The second point to be analyzed is the point 2, where on top of this point 2, which is in correspondence with the water table, so we are exactly here, we have a column of, let's say, dry clay, because we are not considering the capillary effects in here. We believe that there is no capillary effect, so the clay will dry. And we are going to use to determine this pressure, this dry specific weight of 17 kilonewton per cubic meters. The column of clay on top of the point 2 is 2 meters, and this is the reason why we are multiplying here 17 kilonewton per cubic meter multiplied by 2 meters, and we found the pressure of 34 kilonewton per square meter that we can sketch in this diagram as this. And we have the first interval of the first part of this total pressure diagram that starts at 0 at the surface and increase to 34 at the level of the point 2. The next point to be analyzed is the interface between the clay and the sand, and at that point what we have is a column of 2.3 meters of wet soil, a clay in this case, and 2 meters of the dry soil. We analyzed it before. So the formula to establish the value of the total pressure in this case will be 17 times 2, the dry soil, plus 20 times 2.3, the wet soil on top of the 0.3. In total, we will have 80 kilonewton per square meter of pressure at this level, and this is what we show in the sketch of the total pressure. Finally, the last point to be analyzed is the point 4. We are at the end of the sand layer, so on top of this point we have 3 meters of sand, wet sand or saturated sand, 2.3 meters of wet clay, and 2 meters of dry clay. And this is the reason why we have 17 times 2. This is the weight or the pressure produced by the dry clay. 20 times 2.3 is the wet clay, and plus 19 times 3, which is the weight of the sand on top of the point 4. At the point 4, then, we have 137 kilonewton per square meter of pressure, of total pressure. We have defined the effective stress as the difference of total stress and the water pressure. So now, in order to get the diagram for the effective stress, we just need to do the difference between the total stress and the water pressure. For the first point, the point 1, both the total pressure and the water pressure is equal to 0, so then the effective stress will be 0 as well. For the point 2, we are in the water table. We have 34 kilonewton per square meter of total stress minus 0 kilonewton per square meter of water pressure. So then the effective stress is 34 kilonewton per square meter. For the point 3, we have 80 kilonewton per square meter of total stress minus 23 kilonewton per square meter of water pressure. Then our effective stress is 57. Finally, at the point 4, we have 137 kilonewtons per square meter of pressure, of total pressure, minus 53 kilonewton per square meter of water pressure, then we have as an effective pressure 84 kilonewtons per square meter. Finally, in red, you see here the diagram sketched for the effective stress for this simple exercise. Thank you very much.